Good morning. Uh, as promised last class, we're going to talk about another application of heaps besides implementing priority queues. Specifically, we're going to talk about an algorithm called heap sort. This is a algorithm that's like in the same class as quicksort and merge sort. It's a fast sorting algorithm that runs in O of n log n time. And it basically works by taking the array that you want to sort, putting all of its elements inside of a heap, and then repeatedly calling the retrieve max operation to get the largest element, and then the second largest element, and then the third largest element, and before you know it, your array is sorted. Tiny bit more formally, putting the elements of the array inside of a heap, we refer to that as heapifying the array. After we've heapified it, we're going to sort it, and through a bit of trickery, we're going to look at the exact details very soon. We're going to be able to do this without without using any additional space, other than like the, I was gonna say other than the nodes and whatever used to implement the tree, but no, a heap is implemented using the array. We're going to do this completely in place. Say we start with this unsorted array. We want to sort it. As we learned about with the representation of heaps using arrays, you can just sort of convert a array into a complete binary tree. In this case, it's not a very good binary tree. It's not in heap order, and it's definitely not in, it definitely doesn't have the binary search tree property, but it is a tree. We just apply the same rules as before. Where we have the indices of the array representing the positioning of the nodes in breadth first order. Something that we'll have to consider for a heap sort is figuring out where the first leaf in the tree is. In this case, the first leaf is right. In this case, the slides kind of suck. I should probably fix this, but the explanation doesn't seem to correspond to the example. It says the first leaf occurs at index I equals 5. Oh, right. No, the slides don't suck. I suck. We're fine. But basically, we can get the first leaf of the tree using a simple formula that's like along the same lines as the formulas we have for getting parents and children from a node at a specific index. In fact, it's derived from the formula for getting a parent of a node at a specific index. So we don't need to dilly-dally on the details of this. But in general, you can get the index of the first leaf of the binary tree. That is the first node that doesn't have any children, this one, by dividing n by 2 and then taking the floor of the result. So in this case, n equals 11. So we do 11 over 2 equals 5.5. And the floor of that is 5. The heapify operation is another cool instance of something being like kind of sort of recursive, but not actually involving any recursive function calls. It's recursive in the sense that we're solving subproblems and then using those solutions to subproblems to construct a solution to the main problem. We go up the tree starting from each leaf and heapify all the sort of sub-heaps of the actual heap. So within the binary tree that represents the heap, every subtree should also be a heap, and the leaves are subtrees of height 0. So starting off at the leaves, we have a bunch of heaps that only have one node in them, and therefore are already in heap order. Can't really say that for each of these one node heaps, the parent nodes are always greater than the children nodes, but you definitely can't say that they're not greater than the children's nodes. Probably mentioned this, or me and or the markers have probably mentioned this in feedback for certain questions. But this is an example of something being vacuously true. That's a pretty important term in logic that means that something's technically true because no counterexamples exist, even though no affirming examples exist too. A more real-world example is that all of my dogs are over 10 feet tall. It's true. I don't have any dogs, though. I have a cat. You can't point to any of my dogs and say, see, your claim isn't true. So by the rules of logic that we use, it's technically true, vacuously true. And that's the same reason we say that all of these one-node heaps are in heap order. It's just that no counterexample exists. So the first step we get for free. All the leaf nodes are sorted nodes. Or all of the leaf nodes are heaps. So now we go one level up. We heapify the max heap rooted at each node by swapping the root node downward. Again, this was sort of given us for free on the leaf nodes, but now that we've gone one level up, we might actually have to start thinking about this. In this case, 7 is less than both 8 and 9. So that's like super out of heap order. You could swap 8 there, but then 8 is still less than 9, so it wouldn't be in heap order either. So in general, we swap the node downward with the greater of its two children, as long as it's less than one of its children. And then that will result in a sub-heap that's in heap order. We do the same here. This heap is out of order, and we're going to put it back into order by swapping the greater of its two child nodes. Oh, and 11 and 3. We do the exact same thing. Note that each of these requires at most one swap. to restore heap order. And pretty sure we're going to find out that this actually generalizes in a pretty neat way and motivates us to do that recursive thing. There's one internal node with height 2. In the worst case, it would require at most 2 swaps. Like, say that this node was actually 0. You'd have to swap it with 9 and 8, something like that. But it's not 0, it's 10. This subheap is already in heap order, so we can just move on. And then the last node here, the root node, requires at most 3 swaps to restore heap order. In this case, it requires 1. And this is actually the reason why we went bottom up. If we went from the top down, then we would have, yeah, we'd super fail. I guess we'd swap 6 and 10, sure, and then we'd swap 3 and 11, but then we'd have 10 at the root and 11 as its child. Child is less than parent, that violates heap order, but we already did our algorithm. We already went from top to bottom, and we clearly missed a spot. In order to sort of patch this top to bottom algorithm to actually work, we would need a step that also goes from the bottom up. But it turns out you can avoid this entirely by just starting with going from the bottom up. And that works because when you go from the bottom up, it ensures that whatever node you're looking at currently has a heap at each of its subtrees. So at the beginning of this step, we know that the subtree rooted at the root's left child is a heap, and that the subtree rooted at its right child is a heap. This allows us to do these swaps without missing a spot. Here's something that might be a quiz question. Consider an array A of length n. Suppose that it's a power of 2 minus 1. That just makes it a bit easier to do any calculations involving base 2 logarithms, which will definitely come into play. In that case, A represents not only a complete binary tree, but in fact a full binary tree. So imagine we have 4 more indices. Right. I think this might have supposed to have said 2 to the r minus 2. As always, I'll take a look at this after class and correct if necessary. But you can see that if the size of the array is close enough to the size, or to a power of 2, then you'll get a full binary tree, which means that all rows of the binary tree are full. So first up, what's the height of the full binary tree represented by A? So if n equals 1, the height is 0. Then the height is 1 for n equals 2 and 3. And then it's 2 for up to 7 nodes. And this gives us a general formula. In general, if the height is the height is 2 to the r minus 1. Oh, wait. If n equals 2 to the r minus 1, it's r minus 1. You just solve for r using a logarithm, which of course is in O of log n. I'm erasing this because better explanations exist right below what we're talking about, so don't worry about copying my notes. Next, how many entries in A are leaves? Roughly half of them. So you have a full binary tree of height r minus 1. So oh no, I'll just draw my own again. So in a binary tree of height 1, there was 1 internal node and 2 leaves. This doesn't quite give us a pattern. But in a binary tree of height 2, there are 3 internal nodes and 4 leaves. And let me just extend this even more. Now, the binary tree is of height 3. There are 1, 2, 3, 4, 5, 6, 7 internal nodes and 8 leaves. If we were to keep doing this, I think a binary tree of height 4 would have 15 internal nodes and 16 leaves. Every level added to the binary tree basically doubles the number of nodes in the tree. And that gives us that about half of the nodes in the tree are the leaves. This is formalized as saying that there are 2 to the power of r minus 1 nodes in the bottom row. We get that by taking n over 2, basically. I think the floor of it. So to take care of this, remember that exponentiation is repeated multiplication, and that division undoes one step of that exponentiation. So 2 to the r minus, or 2 to the r divided by 2 is 2 to the r minus 1. And then we have a 1/2 here, and okay, I guess I got the floor or ceiling wrong. It should be a ceiling because I knew it was either floor or ceiling because we were disregarding a decimal portion, but I got goofed up a bit by the fact that we're subtracting the decimal portion. So 2 to the r minus 1 minus 1/2 is a number something like 15.5 or 7.5 or 3.5. It's a power of 2 minus 1/2. We have to round it up to the nearest power of 2 for this formula to actually describe what we're seeing. So we do a ceiling. Cool. What's the next thing? Oh yeah, this last one is sort of a generalization of the question of how many are leaves. Now we're asking how many entries of A are at height 1, height 2, how about height whatever? Where the previous question was actually asking us how many entries in A are at length R, I think, R minus 1. So just like we got the number of nodes on the last level by dividing the total number of nodes by 2, we're just going to keep doing that. Again, imagine this was a full binary tree. The last level had about half, just over half, of the nodes in the tree. The level above that is going to have all of the nodes in the bottom level divided by 2. There's one parent for every 2 children. So we just divide by 2 again. Subtract 1 more from the exponent the exponent we're raising 2 to the power of. So last level contains about a half of the nodes. This one contains about a quarter. This one contains about an eighth. And then, according to Zeno, I think, the Zeno's paradox guy, we would go on forever with this stuff. But luckily, the root node is there to save us from that. The root node just has one node, and we can terminate it there. This gives us a general formula that there are 2 to the power of r minus 1 minus k nodes at height k. So that was a bit of a diversion, but this is going to lead into an analysis of the heap sort algorithm. we use our conclusion to that last question to notice that for each level k of the tree, the nodes at height k, of which there are 2 to the power of r minus 1 minus k, all require up to k swaps each. Because, of course, the worst case number of swaps is that you're swapping at every level of the tree. This means that in the worst case, for the whole graph, the worst case number of swaps is k times 2 to the power of r minus 1 minus k, which is to say that every node at that height needs to do the maximum number of swaps. That worst case, I know I just said it's the worst case for the graph, but it's actually the worst case for that level of the graph, which means that to get the worst case number of swaps required by this algorithm, you need to take the formula that we found for the worst case number of swaps at a given level of the tree, and then do a nice little summation. We get the worst case number of swaps at level 1, plus the worst case number of swaps at level 2, plus the worst case number of swaps at level 3, on and on until you get a summation. And then you end up with a summation of a linear function times a exponential function. And that is not something we talked about in class. This specific formula won't appear on the exam, but it's worth mentioning that it exists. We solve this and get that the worst case number of swaps is n minus log base 2 of n plus 1. And then we do some quick real-world style analysis on that. We know that n is in O of log n. Did I say log n? I meant n. And then you could definitely prove this using the asymptotic properties from earlier in the course, or even the definitions if you're crazy and or I tell you that you have to for marks. But the log base 2 of n grows so much more slowly than n that adding or subtracting it to or from n doesn't change the asymptotic growth of that function. So something in O of n minus something in little o of n equals something in O of n. This could be a nice little exercise to do if you're studying, actually. Nothing to do with heaps, honestly, but prove to yourself that that is true using either the asymptotic properties or the definition, preferably both. Finally, we could move on, go back to the actual algorithm. Key point here is that the heapify algorithm runs on an array of length n in O of n time. We have an array, we did a bunch of swaps, turned it into a heap, and that took an amount of time that's proportional to the number of elements in the array. Now that the array has been heapified, we have to sort it. We have the algorithms called heap sort, not heap. Call retrieve max. The retrieve max operation removes the entry with the highest priority and then reheapifies the remaining entries. So now 11 is no longer part of the array. We saved it to some other variable, unless we are content with just emptying the array. An empty array is vacuously sorted. But now the remaining elements have been rearranged enough that they are now in heap order. And as we talked about previously, one call to retrieve max has big O of log n time complexity. We store the retrieved maximum at its correctly sorted location, making it so the remaining heap now has size n minus 1. This would be a real sticking point to pay attention to if you're implementing this algorithm. We had a heap of size 11 before. The indices went from 0 to 10. But now this array is a heap of size 10. Indices go from 0 to 9. And an array of size 1. If we just called retrieve max again on this array without changing its own perception of its size, then this whole array wouldn't be in heap order. We'd have a leaf node with a value greater than anything else in the tree, and the retrieve max operation wouldn't work. So you'd have to have some sort of variable in your code for like heap size or array size or array start index in order to make sure that your heap algorithms only work on the portion of the array that is actually the heap. Do it again. Call retrieve max and then store the maximum value in the appropriate index and repeat until all entries have been sorted. You do this once for every element of the array. So that means that there are big O of n calls to retrieve max. I'd make this even more precise. There are n calls to retrieve max. And this is another thing that you can try proving yourself as an exercise. Doing a O of log n operation n times gives you an algorithm that's O of n log n overall. This slide just says the same thing. Yeah? These elements right here? Yeah, the array is just going to be sorted in ascending order, least to greatest. So we put the second greatest element before the greatest element. And then after one more call to retrieve max, 9 will be gone from the heap. Everything else will be pushed this way. And then 9 would be here. And the final array would look something like 1, 2, 3. Oh, it's just the numbers from 1 to 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that concludes our discussion of heaps. Next up in these slides are the graphs. But as I talked about earlier this week, we're jumping around a little bit. And that means that next we're going to return to a discussion of AVL trees before going on to graphs. This also means that this week's quiz will be mostly about heaps. I have a question about inserting elements into a heap already written because I know that's going to be covered. And then the second question will have something to do with retrieve max, heapifying, or heap sort. And of course, if I can say something meaningful about AVL trees in the next 13 minutes, there will be a question about that too, but I wouldn't bet on it. I'm going to spend some time reviewing the stuff we started with on AVL trees because it's been a while since we last talked about this. We already know and love binary search trees, but we found that if the elements of a binary search tree are inserted in a bad order, we could end up with a binary search tree where most of the nodes are just pushed to one side, and that makes it so all of its operations can run very inefficiently. The worst case runtime for the insert, search, and delete operations depends on how long the longest path is from a root to a leaf. And the length of said path is maximized if the nodes are all just with one child, basically turning the thing back into a linked list and giving us O of n time complexity. We want all of the paths from root to leaf to be the same length because if they're the same length, then the leaf nodes are sort of as divided as possible, and thus the longest path from root to leaf is as short as possible. We solve this in one way using a 2-3 tree. We changed the definition of the tree, and that included like how many values a node could hold, how many children a node could have. And we changed it in such a way that all of the paths from root to leaf were of the exact same length. But it was kind of painful. It's weird and confusing. What we're about to see is another solution to that problem that is also weird and confusing, but in a different way. And that's to sort of keep the structure of the binary search tree intact, but keep track of how balanced it is and rearrange the tree occasionally when it's gotten unbalanced. probably shouldn't have gone as in-depth into that. You've heard all this before. But before we move on, we have to review this too. Key concept for AVL trees is keeping track of each node's height. This node has height 0 because it is a leaf. The longest path from it to a leaf doesn't exist. It's 0. The length of the longest route from Winnipeg to Winnipeg is 0 kilometers because you're already in Winnipeg. This one has height 1 because the longest path from it to a leaf is 1. This one has height 3. Actually, different example. This one has height 2 because the longest path from root to leaf has length 2. There is also a path of length 1 to a leaf node, but that doesn't come into play. Our discussion is only about the longest path from a root to a leaf. And finally, we add another sort of concept of height that doesn't have any intuitive sense, but ends up being really helpful for our calculations. A node that doesn't exist has a height of -1. Sure, there isn't really a driving metaphor I can make here. The distance from nothing to Winnipeg is -1 kilometer. It really doesn't have a real world equivalent. It's just useful for our calculations. We define the balancing factor of a node to be its right child's height minus its left child's height. And we consider a tree to be balanced if the balancing factor of every node in the tree is either -1, 0, or 1. Another way of putting this is that for any nodes, the height of its 2 subtrees differ by at most 1. The tree above is pretty balanced. These 2 nodes are the same height, so they're balanced. These 2 are balanced enough. They're not the same height, but the difference between their heights is -1, which is within our definition for balance. The root is balanced because its 2 children have heights differing by at most 1. But this one, we have a pair of siblings that have a balancing factor of -2. More precisely, we say that this node with value 14 has balancing factor -2. Because it has balancing factor -2, and we just said that we define a tree to be balanced if every node's balancing factor is either -1, 0, or 1, this tree isn't balanced. Doesn't matter that the root node is balanced, there's still that weakness somewhere, and that's real bad. I think that's where we got when we first talked about AVL trees. So I'm going to talk about original content for the next 5 minutes. Crazy. So suppose an AVL tree has height h. We're going to define MH to be the minimum possible number of nodes in this tree. And we're just going to manually determine M0, M1, M2, and M3. So M0 is pretty obvious. There's only one tree with height 0, and it's a single node. There's no other way to do this. So we have clearly that M0 equals 1. For height 1, we're just going to add one more node, and then that'll give us a node of height 1, or a tree of height 1. And we know that it's minimal because we can't take a node away without messing up this height. So maybe this is M3 or M2? Maybe MH equals H plus 1? Now this is a very reasonable guess, but it's wrong. Because we're talking about AVL trees, not binary trees. So in this tree, we have the root node with height 2, this node has height 1, and that node has height 0. Okay. We have an empty space next to the node of height 1, and by definition, it has height -1. 1 minus -1 is 2, so the tree is unbalanced. Because of that, we say that it's not an AVL tree. So to fix this, we're just going to add one more node. It's going to have height 0, and that'll preserve our property that we wanted AVL trees to have. I'm not going to draw the minimal tree of height 3 because I would actually have to draw some stuff above that tree. But for now, you can know that the minimal tree of height 3 looks like this. And there's like a general formula for it, but it's weird. It uses the golden ratio. I don't want to talk about this. So we've seen what it looks like for a tree to be unbalanced, and next class we're going to talk about how to balance them. That's all. Go away.